Those of you who were out for testing yesterday can get more detail on this in the video, but we were looking at the reciprocal function, which is the function 1 over x. And it is our basic, simplest rational function. So we're looking at, in this unit, this new unit, we're talking about rational functions. And that is functions and expressions that can be written as a ratio. And the easiest one is 1 over x. And so yesterday we worked through, see, I don't think I'm muted on here, but let me check and make sure. Yeah, we're good. Yesterday we worked through why this graph looks the way that it does. And I'll let you watch the video to see why that works out. But it has a vertical asymptote and a horizontal asymptote. Remember, an asymptote is that merge line, the line that the graph is getting really close to, but not actually touching. And so we talked yesterday about what happens when we change this equation in certain ways. And we did some work on that. And it looks basically like this. And this is the new page for today. So we talked about this yesterday. We did some examples, but I just want you to write it down in a form that you can look back at it and work from. So when we do transformations on this function, the a number, the h number, and the k number do some different things to the equation and to the graph. And they work very much like what we've seen in other types of transformations. So from what we said yesterday, what does the a do? How does the a affect the graph of this reciprocal function? It's a stretch, it's a dilation. And what we saw is it pulls the graph further away from the origin. So you see that in this function right here, it's kind of squeezed in real close to the x and y axis. A larger number there will pull that away from the origin a little further. So it is a dilation. So the first thing that the a does is a dilation. And when we think about the dilation, what we're going to think about is that we can use factors of that number to help us get specific points on the graph. And I'll show you what I mean by that in a minute. What else can that a number do to the graph? What if it's negative? A reflection, like we've seen in the past. So if we have that a number is negative, it produces a reflection. And if we think about this graph and what it looks like, I'm going to flip back to this page for just a second. What would that look like if we do a reflection? Specifically, let's think of a reflection over the x-axis. So right now where we see it is we have a first and third quadrant piece. And when we do that reflection, that first quadrant piece would flip down to quadrant 4. And that second quadrant piece would flip up to quadrant 3. So it's changing the quadrants that this thing is found in. Up to quadrant 2 is what I meant to say. And so if we remember the numbering of the quadrants, remember it goes like this. First quadrant, you know where that is. And then you go around counterclockwise. You can say if a is a positive number, then the graph is found in what 2 quadrants? Exactly. And if a is a negative number, then the graph is found where? Uh-huh. So that's some stuff we need to recognize. What does the a number do? It produces a dilation or a reflection. In general, if you add a number onto the end of a function, like we've seen all the way through this year, what does that do to the graph of the function? You're going to add a number onto the end. Moves it up or down. And so we can say that this k number that is added onto the end produces a vertical shift. Produces a vertical shift. So what feature of the graph can we see really clearly shifting up as we move it with that K number? Remember, it has a horizontal asymptote. And when we move the graph, that horizontal asymptote is going to shift up and down with the rest of the graph. If you want to draw the graph, the first thing you want to do is draw the guidelines, which are the asymptotes that help you draw in the shape. And so when we do a vertical shift, we're going to move that horizontal asymptote, which we called yesterday HA, horizontal asymptote. It's going to move along with it. Normally, the horizontal asymptote is on the x-axis, which we call y equals 0. As we move it, it's going to change and be y equals whatever that K number is. We're going to remember that we keep the sign. Remember, it goes in the direction that we expect it to. We keep the sign of the K as it shifts up and down. We learned yesterday, question, Lauren? Yeah, so when we have, if you're still writing on this, I'll put it back there in just a second. But we looked at this graph yesterday and we saw as you plug in really big numbers, you are squeezing your answer in closer and closer and closer to 0. That should make sense. 1/10 is a small number, but 100th is even smaller, and 1/1000th is even smaller than that. As x gets large, y gets close to 0. But if you add 5 onto the end of that fraction, and you keep plugging in really big numbers, then those numbers that used to be close to 0 are now going to be close to 5. It's squeezing the graph in now close to 5 instead of close to 0. Does that make sense? So we're just taking every output number and adding 5 to it, and that takes the whole graph and shifts it up by 5 units. And it takes that asymptote that is the guideline for the graph and also shifts it up 5 units. We also noticed yesterday something about the range of this graph. You know, it goes down forever, right? It goes up forever. But in the middle, what happens? Is there a number that is not included in the range of this? It's never going to get to 0. So the range of this skips over the number 0. And so if we shift it up, it's not going to necessarily skip over 0. It's going to skip over wherever that K number is. So on this function, the range will be all real numbers except whatever that K number is. If the K is positive, except for K. If it's like -6, then except for -6. Does that make sense?
So how would I write that?
You can write exactly what I just wrote, all real numbers except 5. Or you could say X is not equal to 5. Or if you wanted to write it in interval notation, you would do, remember parentheses means not included. So we would do -infinity up to 5, but not including 5, with parentheses, union 5 to infinity. So basically what that does is it includes everything from -infinity to infinity, except that one number 5.
What the range was like? I know it's the X stuff.
Yeah, so we'll look at the X stuff now. We'll look at the X stuff, and that's going to have to do with this H, which is going to produce not a vertical shift, but horizontal shift. And when we shift horizontally, it's not going to move the horizontal asymptote. It's going to move the vertical asymptote. That should make sense to you. When you move something across the page, a vertical line is going to get shifted across the page horizontally. When you move something up and down the page, a horizontal line is going to get moved up and down. And so vertical asymptote will be X equals whatever that H number is. Remembering that that's going to change sign. That's what the negative indicates in the formula. X minus H, that's saying that the number we use is going to be the opposite of the H. And the way that this is easy to remember is that number where the vertical asymptote is not included in our domain. the domain is all real numbers except for the H number. And that makes mathematical sense because it's where the asymptote is, but why does it work that way? Mathematically speaking, like if we think about the calculation, that what would happen, like if we had something like x minus 2 in the denominator, if I try to plug in 2, what happens with the calculation? I would get a 0 in the denominator of that expression. And you learned a long time ago that you can't have a 0 in the denominator of an expression. That calculation can't be done. So we cannot have any input value that will produce a 0 in the denominator. And so if we have something that's producing a 0 in denominator, that's going to be excluded from our domain, and that's going to tell us where the vertical asymptote is. So all that's a review from yesterday, but just kind of put into some language that you can look back at and understand. Does that make sense? We'll do an example to demonstrate that real quick. So probably 2 examples, since a lot of you were gone yesterday. What if we have -1 over x minus 1 plus 2? Okay, so A is negative, so that's in the top left and bottom right, which is called quadrants 2 and 4. So it is in quadrants 2 and 4. That's going to be important to notice. So what else do you notice?
The range will be all real numbers except 2.
Yeah, except 2. And so significantly when I'm drawing the graph, I'm going to pay attention to that 2. And what am I going to draw where I see that 2? Horizontal or vertical? It's the vertical shift, but it's the horizontal asymptote. Does that make sense? You can't just learn the word horizontal or vertical. You got to learn what you're doing. It's the horizontal asymptote shifting up by 2 units. So the horizontal asymptote will be found where y equals 2. I'm going to draw a dotted line where y equals 2. That's going to be the boundary line as I'm drawing the graph going out, thinking about the end behavior. Does that make sense? And then what else? We're going to move it to the right one, which means I'm going to take a vertical asymptote and sketch it in where x equals 1. And so that's going to look like this. Does that make sense? So we have vertical asymptote, we have horizontal asymptote, and now we want to sketch in the graph. And when I say quadrants 2 and 4, just for a minute, I want you to visualize this thing as if the blue line and the green line are the axes for your graph. And so picture 2nd quadrant and 4th quadrant from there. Does that make sense? And so if you want to find some specific points to help you draw the graph, go near the vertical asymptote and plug in an x number near there. So what should I plug in for x? 2 or 3? If I plug in 2, I'm putting 2 where the x is. So the denominator is equal to 1. -1 divided by 1 is -1 plus 2 is 1. -1 plus 2 is 1. That's the ordered pair 1, 1. Or sorry, we plugged in 2 and we got 1. So it's right there. With that red dot right there, can you see what this graph is going to have to look like? If you understand the shape we drew yesterday, you should see how that's going to squeeze upward towards the vertical asymptote, and it's going to go downward. I'm sorry, squeeze upward towards the horizontal asymptote and downward towards the vertical. And you're just going to do a rotation of that into the other quadrant. If you want to see a specific point, what should you plug in? 0 would work. It's to the left of the vertical asymptote. And if we plug in 0, we get -1 in the denominator. -1 divided by -1 is +1, added to 2. We plugged in 0, we got 3 for our answer. And from there, you can see how to sketch in the graph of that basic shape. So I only had to do calculation on 2 points to find a pretty complicated graph, because I used what I know about the patterns we learned yesterday to build the shape of this thing. And then I used a couple of specific points to kind of get the idea of how to sketch it in around those asymptotes. Does that make sense? Want to do one that has an A number that's bigger than that. So one more example. We'll do g of x down here equals 6 over x minus or plus 2. Tell me what you know.
First,
Okay, so several things. Vertical asymptote, -2. I heard that, so we'll go ahead and sketch that in. It is in quadrants 1 and 3 because the A is positive. Yes. We don't have a vertical shift, so the horizontal asymptote is in its standard location, which is y equals 0. It is the x-axis. All real numbers except 0, and the domain is all real numbers except -2. I did that wrong, didn't I? What did I do wrong? I put the vertical asymptote at +2. It should be over here at -2. I wrote -2, but I drew it in the wrong place. Does that make sense? So I know I'm going into quadrants 1 and 3. I just need to find some specific points now. Yes. You could plug in 4 because that's easy to divide by 6. If you plug in 4, you're going to get 1. So 1, 2, 3, 4, 1. There we go. Plug in numbers that are going to give you an answer that's evenly divisible by 6. If I plug in -1, I'm going to get 6 divided by 1, which is +6. So it's going to be up here. I can plug in 0. That's easy, isn't it? What do we got? 3. Is that enough to get a good idea of what this graph looks like? So we're going to go up towards the horizontal asymptote and down towards, up towards the vertical, down towards the horizontal. What's different about the shape of this one as opposed to the one above? Stretched out away from the x-axis some more. And you can do a similar idea on the other side. You know, plug in something like -4 would be good. If we plug in -4, we're going to get -3. So it's going to be right there. If we plug in -5, we're going to get -2. And from there, you can see a pretty reasonable shape of how it fits in. Does that make sense? So you do need to show me some specific points on the graph. Do that smartly. Don't just plug in random numbers and connect the dots. Look at the vertical asymptote. And so one of the ways that I can figure that out is the vertical asymptote is at -2. Give me a number that's an easy factor of 6. 3. Count 3 units away from the vertical asymptote. That will give you a number that's going to be evenly divisible by 6. Does that make sense? But if you plug in just a few numbers to see the basic shape, it will give you an idea of the graph. So that's all I want to do with graphing today. We'll review it a little bit more next week. For those of you who haven't had a chance to watch the video, if you weren't here yesterday, make sure you do that. Are there questions on graphing? So I want to spend the rest of the day working on simplifying rational expressions, which is like simplifying fractions. I want to start with this. You don't have to write this in your notes, but if I want to simplify this fraction, this is more like a middle school problem, not an algebra 2 problem. Really, even before middle school, you learned how to do some of this. How do you do that? How do you simplify that fraction? You can see that top and bottom are both divisible by 5. If you have a hard time figuring out how to divide that by 5, it's helpful to just do a factor tree on both of those numbers. So let's do that real quick. 175 and 70. I know some of you struggle with calculation. I'm going to try to give you some things that help you with calculation, because a lot of this is going to be done without a calculator. You need to get more comfortable without a calculator. If you're trying to find a factor tree on 175, think about money. Think about how many quarters it takes to make $1.75. How many quarters do you need for $1.75? So it's 7 times 25. and then it's 5 times 5. Does that make sense? And then 70 is what? 10 times 7, 5 times 2. So we can write this as 7 times 5 times 5 divided by 7 times 5 times 2. What's nice about that? The 7s and the 5s cancel out. You know that, and you've always done it, but do you understand why? Because understanding why is what's going to help you do well with this unit. They equal 1. If I take this thing right here, it equals 1. And if that's a 1 that's multiplied by everything, and that doesn't change the value of it. So I can just take it away because 1 times the rest of that stuff is just equal to what we started with. And I can do the same thing with the 5 there. And so I'm left with what? 5 halves. So that fraction simplifies to 5 halves. I'm going to show you something right now that you're going to look at and you're going to say, well, duh, I wouldn't do that. But when you mix it in with variables, some of you are going to do this. Here's something that looks kind of similar to that, but it means something completely different. 7 plus 5 plus 5 divided by 7 plus 5 plus 2. Same numbers, different operations. Can I cancel the 5s and the 7s? They're added. I can't cancel things that are added. If I did, that would simplify to 5 halves again, wouldn't it? But what is that number on top? What is that number on bottom? Is that number something I could simplify? When you simplify, you look for factors of the number. And 17 has no factors, it's prime. And the factors of 14 are 7 and 2, which don't cancel with the 17. So there is no way to simplify that fraction. You cannot just cancel numbers that are added. Like I said, you look at that and you're like, well, I wouldn't do that. But it's easy to get things confused when you see algebraic expressions. So we need to keep that in mind as we look ahead to this page in your notes. It says Introduction to Rational Expressions. If you have that, get it out. If not, you can just take notes on paper. We're talking about rational expressions. When we did graphing, we saw the most simplified, easy rational expression we can work with, which is just 1 over x. A rational function is a ratio. That's a real simple ratio, 1 over x. In general, we can say a rational function can be written as a ratio of, y'all are going to love this word. Remember this? Collective groan. One good thing about doing this unit right at the end of the year is polynomials was the first unit for this semester, and it's been a long time since we've done polynomials, and it's going to be tested on your exam. So we're going to have to review a lot of that polynomial work as we are working on rational expressions. When working with a rational expression, it is extremely important to understand the difference between terms and factors. When we were learning about polynomials, what did we say terms of a polynomial are? The number before a variable is called a coefficient. It's part of a term. 2a plus b plus c or whatever. It's those things that are separated by what? What comes in between terms? What kind of sign? Really just 2 of those, addition and subtraction. The signs that come in between terms are addition and subtraction. Terms are things that are added and subtracted with each other. So terms are separated by plus or minus. An example of something with terms that we can clearly see is this. This has 3 terms. We see terms very clearly when it is in standard form. Remember, we talked about standard form of a polynomial is when we have all the variables stretched out with an exponent on each one of them and they go in order from highest to lowest. We're putting the terms in order. So the terms of this expression are x squared, 5x, and 14. They are separated by pluses and minuses. What's the difference between that and factors? What does it mean that 5 is a factor of 35? It divides it evenly. And so you can write it as two numbers multiplied together to equal 35. 5 times 7, those are factors of 35. Does that make sense? We're talking about multiplied things. Factors are separated by what? Factors are separated by multiplication. When you're looking at multiplication, that's when you're thinking about factors. The problem with rational expressions is we're mixing together addition and multiplication. So you have to figure out where the addition and the multiplication are. So as we go through this today, if you see something that's surprising and you say, oh, I thought we would have done it that way, I want you to mention that so that we can address that issue and say, this is why it's done this way. Because I want to clear up those questions and those things that don't seem to fit with what you might have expected as we go through it. So factors are separated by multiplication. Can I factor that expression that I wrote in red? What multiplies to negative 14? Yeah, 2 and 7. X is plus 7 and minus 2. So the factors are these two things. And so this is factored form. When you are working with rational expressions, you want to see things in factored form. Most of the time they're given to you in standard form. So the first thing you're going to want to do is factor. Don't do any work until you factor. Always look at the top and bottom separately first. Don't just jump in and start trying to cancel things without factoring the top and bottom separately first. No. So just like when we looked at that number 17/14, it's not reducible, but we need to look at it and say, can I factor it and find anything that I can reduce first? And so if you can't find anything that factors out of it, then you can't reduce it. So start by factoring the numerator and the denominator separately using methods that we've learned. And so we'll be reviewing some of those factoring methods today. Simplifying rational expression. First step, what do we always do? First step, factor, numerator and denominator. Y'all, I write this stuff in the notes for a reason. And a lot of times when you're studying, your eyes go past those steps and just look at examples. But if you look at those steps, it's telling you, this is what I need to do first. I always need to do that first. And I'm going to get confused if I try to do something else first. So factor the numerator and denominator. I'm going to give you a couple of examples of how to simplify rational expressions. So 5x squared minus 20 over 4x squared plus 12x minus 8. So there's a much more complicated rational expression than the ones that we've seen up to now. Tempting. 20 on top, 8 on bottom. They're both divisible by 4. Let's cancel out a 4. Can I do that? Those are terms, not factors. Do you see how things here are separated by pluses and minuses? This is in standard form. I can't do that. Don't try to cancel first. What should I always do first before I try to do anything else? So how do we factor the numerator? Factor out of 5. And we're left with, we're good with that? Let's go further. Can we factor that x squared minus 4? Exactly. So we're going to see a lot of that difference of squares factoring, and that ought to be quick and easy. You ought to recognize it real fast. Denominator may be a little harder, but what do you notice? So we've got x squared and 3x and minus 2. Let's do this. I actually wanted that to be a plus. I wrote the problem wrong, and it won't be factorable if I don't leave a plus there. So change that, make sure you get the plus. Can we factor x squared plus 3x plus 2? Well, x plus 2, x plus 1. Let's bring over the 4, not forget that. X plus 2, x plus 1. So the first thing we do is treat the top and bottom like two separate factoring problems And then we can look at it and say, what will cancel? We now have factors. We need to look at things that are separated by multiplications and we can cancel those. So what's common on top and bottom? Anything else? So what that means is I'm left with, in the numerator, 5 times x minus 2, and in the denominator, 4 times x plus 1. You could go ahead and distribute that and write it as 5x minus 10 over 4x plus 4, and that's fine, but you don't have to. It's fine to leave it like this. I'll take it either way. So we factored the numerator and the denominator. We canceled what's common on top and bottom. Restrictions on the domain. What do I mean by that? Remember when we were talking about the graphs, we said you can't have a 0 in the denominator. In these expressions, we can't have a 0 in the denominator. So we have to look at the denominator and see what would make it 0. But very important, we are looking at the original denominator, not the denominator of that simplified canceled expression. So go back to the original denominator in its factored form. That's going to tell you restrictions. What numbers can we not plug in that would make that denominator 0? Close. -2 and -1. Change the signs there. Those would be the numbers that make that equal to 0. Does that make sense? I can't plug in -2. I can't plug in -1. Those would make the original denominator equal to 0, and I can't have that. So, questions on that problem?
So when we're gonna solve it, you're gonna say simplify and tell me restrictions.
Yeah, simplify this this rational expression and what are the restrictions on the domain. So here is another one. X squared minus 9 over 3 minus x. Can I cancel the 3 with the 9? Can I cancel the x with the x squared? Don't cancel factors, or don't cancel terms, cancel factors. I don't have factors right here. I need to factor it. What do I do on top? So that's easy factoring on top. On bottom, yeah, close, not quite. It depends on whether you're thinking about a parentheses there, Lauren. Will I be able to cancel 3 minus x with x minus 3? It's so close.
No.
If it had said 3 plus x, would I be able to cancel that with x plus 3?
Yes.
I can rearrange the order of addition. I can't rearrange the order of subtraction exactly, but it's so close, there ought to be something I can do. When you switch the order of subtraction, 5 minus 2 versus 2 minus 5, what does that do to your answer? The only thing it does is changes the sign. And so when I switch x minus 3 to 3 minus x, the only thing that does is changes the sign. What I can do here is factor out a -1. If I see that it almost matches, but not quite because it's reverse subtraction, then I can factor out a -1. What do I get when I factor out the -1? The x becomes positive, the 3 becomes negative, right? And now that's a little easier to work with, isn't it? So what's my answer? The negative can move up to the numerator. It doesn't matter whether it's in the numerator or the denominator. So there's no point in putting divide by -1. We'll just put -1 times that. If you were to write -x minus 3 with no parentheses, that would be fine. I'll take it either way. That doesn't have a denominator. Are there any restrictions here?
We have to go back to the original.
Doesn't matter what you have in the final answer. If you can't plug it into the original, You can't plug it into the simplified version. So look at the original and say, what would we not be able to plug in right here? Is it 3 or is it -3? X can't be equal to +3 because +3 is the thing that would make it equal 0. Make sense? One more real quick. If you see this 24 x squared y cubed over -8 x cubed y squared, I want you to think for a little bit about how this is different from the previous problems we've done.
You can't make groups. That is,
What do you mean by groups?
like, if you can find a common denominator, which would be like 4 or 2,
Mhm.
you can't do groups like how we do last
Okay.
chapter.
Yeah, so we don't really need to be thinking about the groups when we're thinking about just canceling. We just need something common on top and bottom. And we see that there is some stuff common on top and bottom. But how many terms do you see within this? A lot of times have people say, oh, it's 3 terms on top and 3 terms on bottom. But what did we say separates terms? Pluses and minuses. Do you see any pluses and minuses here? All of this is one single term. And that means everything you see is already a factor. This means 24 times x squared times y cubed. Everything's already a factor. So in some ways, it makes this problem easier than some of the ones that we've just done. And so we can say this is one single term on top and bottom. So the way that we approach it is a little different, and you need to pay attention to the difference here. If you're not paying attention to the differences between how this one works and how another one works, then you get a little bit confused by it. Let's think about what all is multiplied into this expression. In the 24, I see there's some cancellation that can happen between the 24 and the 8, right? How can I break down the 24? You can break it down further than that, but is there any need to? I've got that 8 on top and I see an 8 on bottom, and that's going to cancel. So I don't need to break it down any further than that. I'm going to write this as it means 8 times 3 times x times x times y times y times y. You do not have to write that out, but you should think it out. You should think about what that means. It means all this stuff multiplied together. And on the bottom, -8 times x times x times x times y times y.
You just do 8 times -1.
You could write it as 8 times -1 also. And actually that may help you see a little bit better what's going on there. So -1 times 8. There you go. What can we cancel? 8's cancel. X's cancel. Y's cancel. And so we are left with a 3, a -1, a y, and an x. I'm gonna write it like that. Doesn't matter whether negative goes on top or bottom, but it's a lot nicer to write it on the top or out to the front. So -3y over x. And that's much simpler.
Oh, you know, I see. You moved the negative up all the time.
Exactly. It doesn't matter whether the negative goes on the top or the bottom. So that's the answer. What about restrictions? This one's different also because it has an x and a y. So let's look at both of those things. What numbers would make the denominator equal 0? 0 for x and also 0 for y. I can't plug a 0 in for x. Does that wipe out the denominator? I can't plug in a 0 for y because that also would wipe out the denominator. Does that make sense?
How would it wipe out, from the original one, how would it wipe out the bottom with the -8 there?
Because -8 times 0. Yeah, so keep in mind that what we're doing is multiplying. Paying attention to the operations and the difference between addition and multiplication is extremely important. And when you throw the variables in there, it gets a little confusing. So you've got to pay very careful attention to that. I want to take just a second to let you look at a couple of practice problems, and then we'll do a little bit with multiplication. This is on page 446, I think. Let me see, 446, but you don't have to get your book out. You can just look at it right here. Take about 3 minutes. Do A and B. C is very much like one we just did in your notes. So you can do with A and B.